Hello again. Thank you for studying math with me and for watching this video. Is Newton's method. This is best watched with pencil and paper and using remote controls in YouTube. Play, pause, and rewind. You may recall that we previously in this course used the intermediate value property for continuous functions to approximate the root of a function. That's also the solution of the function f of x is equal to 0. That approach used the continuity of the function and was called the bisection method. It reduced the error in every iteration by a factor of 2. And that was good, but it's possible to do much better. Today we consider another method, more sophisticated and more powerful. As with all technology, the fancier the tech, the frailer. It is called Newton's method after Isaac Newton and will be in the scope for the comprehensive final exam. So here is the situation. We start with a red function shown here, y equals f of x. And you can see that the root or the solution of f of x is equal to 0 is this red dot here. And so we're going to use Newton's method to approximate that and develop a sequence that will converge to that point. And we start by guessing something to be x0. And so we make a guess, and this is the guess that we're making in this figure. And then we use the technique we talked about in the linear approximation to a function to find the equation of the tangent line shown blue in here for x0. So the tangent line at x0 is blue, and we learned that at point x0, the tangent line of this is given by the y coordinate is equal to f of x0 plus f prime of x0 times the whole of x, the variable, minus x0. So that's the equation of the tangent line. And Newton's reasoning was, well, the tangent line is a good approximation to the function, so maybe I will see where does the tangent line hit the x-axis. And so we can do that, and we do that by taking the equation of the tangent line, setting y to be 0, and solving that for a point called x1. And x1, solving this equation, is x0 minus f of x0 divided by f prime of x0. And that is this point here, and you can see that's a better approximation than our initial guess x0. So x1 is closer to the red dot than the first one. But we can do that again, and we do that again by using the approximation that now is drawing the tangent line curve, but the tangent now is at x1, which was where the first approximation gave us as approximation to the red dot. And again, we can then set y equal to 0 in the equation for the tangent x1. And again, we're going to be using the approximation here that we have. Well, x2, when we look at the equation of that, is going to be x1 minus f of x1 over f prime at x1. And so you see, as we take more and more of these approximations, the limit as x tends to infinity ends up being closer and closer to the red curve. At least that's what we hope. And here is Newton's method stated in its full glory. If xn is an approximation of a solution of f of x equals 0, and provided that f prime of xn does not equal to 0, because no one can divide by 0, the next approximation is given by xn plus 1 is equal to xn minus f of xn over f prime of xn. And this is known, my dear students, as a recursion relationship. Let's look at an example. Here we want to use Newton's method to determine an approximation to the solution of cosine of x is equal to x that lies in the interval 0 to 2. And we're being asked to find this approximation to 6 decimal places. And so we will be using technology Excel or some calculator to do this. First, note that we weren't given an initial guess, and one of the rules we talked about when we were doing the bisection technique is, well, the middle isn't a bad guess, so we're going to take our initial guess, x0, to be equal to 1, the midpoint of 0, 1. And also, recall, we must have the function in the form f of x is equal to 0. Therefore, we first are going to rewrite this equation as cosine x minus x is equal to 0. Now, a solution to this one is a solution to cosine x equal x and vice versa. So this is certainly fine. We can now write down the general form for Newton's method that I just showed you. Doing this will often simplify the work, and so it's not a bad idea to do this. Remember that xn plus 1 was equal to xn, the previous value, minus, this was f of x, when we were substituting the previous value xn into it. So the function is this one equals 0, we're trying to solve. So we write f of xn is equal to cosine of xn minus xn. And then we divide this by the derivative. Now the derivative of this is going to be negative sine minus 1. And so we have to divide this by negative sine xn minus 1. So here was the recursion relationship that we have, and we can now get our first approximation. Remember that x0 was 1, that was our guess, and so we compute x1 equal 1 minus, this is cosine 1 minus 1, all over minus sine of 1 minus 1. And again, this is a calculator kind of thing. Again, cosine of 1 and sine of 1, the 1 there is in radians. And so we do this calculation and we get this number. Now we should point out that the phrase 6 decimal places does not mean we just get x1 to 6 decimal places and then stop. Instead, we continue until 2 successive approximations agree to 6 decimal points. So we need to do this again. So we're going to do x2 is going to be x1, and so x2 is going to be x1 minus, and we use the previous values for xn. So you see this is going to be the cosine of, and this is what x1 was, minus x1 divided by the negative sine of x1 minus 1. And we do the calculation of this again and getting this. Now we are making progress because now we have the approximation correct. I mean this one and this one agree on the first decimal point. So let's do another one and see what happens. Well, if we do another one, we will have x3 is equal to 7390 and so on and so forth. And so now we've got it to 3 decimal places because this one and this one agree on the first 3 decimal places. We need at least one more. We do the same calculation again, and we get x4 is equal to 0.739 and so on and so forth. And now we've got 2 approximations that agree to 9 decimal places. You see these agree to 9 decimal places. We want it to be good to 3 decimal places, and so we can stop. So we say the approximate solution is x4 is equal to this. Now, this next example is a little silly because we know the answer. If you have the cube root of x equal to 0, you know that the solution of that is just x equals 0. But what we're going to do is see what happens. And we're going to use x0 equal 1 to be our initial guess. Now, it is a silly example, but it makes a very important point. You see, this technology is fragile. Sometimes it works and sometimes it doesn't. Let's first get the general formula for Newton's method. So xn plus 1 is going to be xn, and then this is going to be f of xn. Well, that's going to be f of the cube root of xn, or xn whole raised to the 1/3. But then we're going to divide by the derivative. Well, the derivative of this is going to be 1/3 xn to the minus 2/3. So that's what we're dividing by. And if you simplify this using the laws of exponents, you will get that xn plus 1 is equal to xn minus 3xn. And if you calculate that, that's minus 2xn. Now, we really don't need to do any computations here. These computations get further and further away from the solution. And so here you can see that you get 2, minus 2, 4, minus 8, 16. And so this fails, and in fact fails spectacularly. So you do need to be careful with Newton's method. It usually will quickly find an approximate solution to the equation. However, there are times when it will take a lot of work, and others that it will not work at all. In closing, time is precious. Each day must count. Do the math. It will make you strong. And God willing, I will see you on Monday.